So you'll recall in the last video, we took a look at the curve y equals x squared, and we estimated the area under the curve between x equals 0 and x equals 1 by doing a left-hand sum and a right-hand sum, dividing the interval 0, 1 up into 4 equal parts. We're going to do something similar today, except at the end of it, we're going to end up with the exact area under the curve. So the first thing I want to do is divide the interval up into n equal parts. So if I take the interval 0, 1 and divide it up into n equal parts, so y 0, 1, because we're going from x equals 0 to x equals 1. I'm not specifying what n is, it's just an arbitrary number. So the first dividing line is going to be 1 over n. The second dividing line is going to be, let me move this over a little bit more so you can see better. So 1 over n, 2 over n, 3 over n. We don't know whether n is 4 or 10 or 50 or a million, dot, 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 all the way up to this second last one is going to be n minus 1 over n. That would be the second one. Like if n was 10, that would be 9/10. And this last one, 1, is just n over n. So those are our dividing lines. Just like we had before, we did this with n equals 4 equal parts. This time I'm not specifying what n is. And on each of those parts, just like last time when we did the right-hand sum, I'm going to do a right-hand sum here. We're going to construct a rectangle which touches the curve on its right-hand side. So that first rectangle touches the curve where x equals 1 over n. And that second rectangle touches the curve where x equals 2 over n. The third rectangle touches the curve where x equals 3 over n. If there was a fourth, there's a fourth one, a fifth one, the fourth one would touch the curve at 4 over n, 5 over n, 6 over n. The last one's going to touch the curve on its right-hand side, so n over n at 1. So let me do my best to draw this. Apologize in advance for the wonky drawing. Oops, that is wonky. That's supposed to be a rectangle. Use your imagination. And it touches the curve at x equals n over n, or 1. Now we can figure out the total area of all these rectangles. The first one we said touches the curve right here. Its x-coordinate was 1 over n, and this curve, I happen to pick the curve y equals x squared. I want the area under the curve under y equals x squared. We could do this with a different curve. Right now, we're doing y equals x squared. So if the x-coordinate is 1 over n, the y-coordinate is going to be 1 over n all squared. And that's going to be the height of the first rectangle, the y-coordinate of the curve at that point. The second rectangle touches the curve at 2 over n, and its y-coordinate is going to be 2 over n all squared. The third rectangle touches the curve at 3 over n, x equals 3 over n, and the y-coordinate is going to be 3 over n all squared. Fourth rectangle, fifth rectangle, sixth rectangle, all the way to this last rectangle, which touches the curve at 1. I'm going to write that as n over n for reasons which will become obvious later. And its y-coordinate, 1 squared is 1. I'll write that as n over n all squared. So let's go ahead and write down an expression describing the total area of all these rectangles. So this is a right-hand sum. We're doing a right-hand sum here, just like we did last time. Last time, our sum had 4 terms in it because we had n equals 4 equal subintervals. This time I didn't specify, so our term is going to have our sum is going to have n terms in it. N rectangles, n terms. How wide is that first rectangle? Well, it's 1 over n units wide. In fact, they're all 1 over n units wide. And the height of that first rectangle, we said that was 1 over n squared. The second rectangle, it's still 1 over n units wide. And its height is 2 over n all squared. The third rectangle, its width is still 1 over n. They're all 1 over n in width. And its height is 3 over n all squared. Plus, and so on, and so on, and so on, till we get to the last one. Till we get all the way up to the last rectangle, its width is still 1 over n, and its height is n over n all squared. And you can see that we do indeed have n terms here. We have the first one with a 1 here, the second one with a 2 here, 3, 4, 5, all the way up to n, whatever n happens to be. So let's do a little bit of simplification here. First of all, I'm going to bring the exponent into the fraction. We know that exponents distribute over multiplication and division. Here we have division, so we have 1 over n times 1 squared over n squared plus 1 over n 2 squared over n squared plus 1 over n 3 squared over n squared. I don't know why I didn't put that in parentheses, not that it really matters. Plus all the way up to 1 over n squared over n squared. And now in each of these terms, I have an n here and 2 more n's on the bottom here. So each of these terms, this first term I can really write 1 squared over n cubed, 2 squared over n cubed, 3 squared over n cubed, all the way up to n squared over n cubed. I'm going to factor out the n cubed, the 1 over n cubed. So 1 over n cubed. In this first term, all I'm left with after I take this n and those 2 n's out is the 1 squared on top. And over here, after I take that n and those 2 n's out, which I did, I'm left with 2 squared on top, and then 3 squared on top, and then so on, all the way up to n squared. Well, that's already looking better. Okay, now what I want to do is see if I can simplify that. If you think back to a previous lecture, you remember that we had a formula for the sum of the first n perfect squares. Let's go ahead and use that now. So 1 over n cubed, and if you recall the formula for the sum of the first n perfect squares, it was n times n plus 1 times 2n plus 1 all over 6. So what we have here is n times n plus 1 times 2n plus 1 all over 6n cubed. I can simplify that a little bit more without doing too much work. I can cancel this n with one of these on the bottom, so that goes away, and I'm left with a n squared. So what I have here is an n plus 1 times 2n plus 1 all over 6n squared. That's pretty amazing already, that we have such a simple formula which tells us the total area underneath all these rectangles. Now, it's clear looking at this picture that no matter what n is, we have overestimated the area underneath the curve. But remember our discussion at the end of the last video, that you can see that if we have a lot of rectangles here, while each of these rectangles goes above the curve, they don't go above the curve much. When we had n equals 4 rectangles, each rectangle stuck out above the curve a lot. If we did n equals 10 rectangles, they stuck above the curve less. N equals 100, even less. N equals 1,000, even less. And so you might be already catching on to what we're about to do. We are going to let the number of rectangles grow and grow and grow. We're letting n get very big. And as n gets bigger and bigger and bigger, so if we have these really narrow rectangles under here, they stick above the curve hardly at all. And the bigger n gets, the closer they get to the true value of the area under the curve. So what we're going to take a look at, so the true area under the curve will be the limit as n goes to infinity of the total area underneath all the rectangles, which we have made very nice over here. N plus 1, 2n plus 1, all over 6n squared. The limit as n goes to infinity of n plus 1 times 2n plus 1 all over 6n squared. So as n gets bigger and bigger, the total area under all the rectangles gets closer and closer and closer to the total area under the curve. Let's go ahead and evaluate this limit. We have techniques to evaluate this limit. Let's multiply the top out. So this is equal to the limit as n goes to infinity. When we FOIL the top out, we end up with 2n squared plus n plus 2 more n plus 3n plus 1 all over 6n squared. So 2n squared plus 3n plus 1 all over 6n squared. We know a trick when n is going to infinity or n is going to minus infinity. I'm going to continue that up here. What we do is we multiply the top and the bottom by 1 over the largest power of n. So let's go ahead and do that. So I'll multiply the top by 1 over n squared and the bottom by 1 over n squared. And if I do that, 2n times 1 over n squared, so let me write my limit first. Two n times 1 over n squared is 2. 3n times 1 over n squared is 3 over n. And 1 times 1 over n squared is 1 over n squared, of course. That's what I have on top. And on the bottom, I have 6n squared times 1 over n squared. The n squareds cancel out. I'm just left with 6. And as n gets bigger and bigger and bigger, 3 divided by n gets closer and closer to 0. 1 over n squared gets closer and closer and closer to 0. This whole expression gets closer and closer and closer to 2 over 6, or 1 over 3. And we were able to determine the exact area. This was the true area under the curve y equals x squared between x equals 0 and x equals 1. It is exactly 1/3. And this business about using the limit is what makes this calculus. We saw that when we were looking for the slope of a tangent line, we needed a limit for that. Anything with a limit is calculus. And over here, we started off with a sum of rectangles. That wasn't calculus. But as soon as we put a limit in front of it and let the number of rectangles get bigger and bigger and the rectangles get narrower and narrower, then we were able to determine the exact area underneath this curve.